So thank you all for joining today. It is my pleasure to introduce Professor Nidhi Rajput from the Department of Material Science and Chemical Engineering. Nidhi came to us actually from Tufts not too long ago. She's been an excellent addition to the department at large and to the chemical engineering program. And prior to that, she did her PhD work in chemical engineering at Louisiana State University, specializing in molecular dynamics studies of ionic liquids. Now she's expanded on that quite a bit, and her group efforts are divided between density functional theory and large-scale classical molecular dynamics simulations. And most recently, just to highlight, I think, some of the work she's going to talk about today, she published a paper in Nature Computational Science on automatic frameworks for high-throughput predictions of NMR chemical chips within liquid solutions. So yeah, with that, I'll turn it over to Nidhi and Robert. I have to unfortunately hop off. So maybe you would be able to handle the Q&A at the end?
Yeah, I'd be delighted to. Yeah, thank you.
Great, thank you. Take it away, Nidhi.
Okay, thank you so much, Jason, for a very kind introduction, and good afternoon, everyone, and thank you so much for joining us for this seminar today. So I'll be talking about the work in my lab, which is focused on using molecular simulations to understand structure and property relationships and in materials and designing optimal materials for different applications. So this talk is broadly divided into two parts. I'll first discuss the details of the two open source code base developed by our lab. The first one is for performing high throughput multi-scale simulations. This infrastructure is called MISPR, which stands for Materials Informatics for Structure Property Relationships. I'll give you some flavor of some of the density functional theory and molecular dynamics simulation-based workflows to compute different electronic, structural, and dynamical properties. And the second code base is called MD-Prop2, which is a standalone code, which allows us to perform a bunch of different structural and dynamical analysis for MD simulations. Okay, and then I will show you the applications of MISPR and MD-Prop2 for accurately predicting solvation environment in complex liquid solutions, as well as for doing high throughput screening for electrolytes used in lithium sulfur batteries. But I would like to start with just giving you a very brief idea of why and how urgent it is to start utilizing the power of electricity and explore sustainable, clean energy resources. So as scientists and engineers, we care a lot about data. If you search online about global warming data, this is probably the first few links that you would find, which shows that we are emitting greenhouse gases at a very alarming rate. And these gases are rapidly increasing Earth's average surface temperature, which leads to extreme weather conditions such as high intensity and frequency of floods, snowstorms, wildfires, etc. Unfortunately, these extreme weather conditions do not only cost us billions of dollars, but also thousands of lives each year. At the heart of the problem is that we still rely on these dirty carbon-based fuels for almost 80% of all the energy that we generate each year. And on the right-hand side, you're looking at the energy consumption chart, and you would notice that there are three large sectors: electricity grid, transportation, and industry, which consumes 90% of all the energy that we generate each year. So one can imagine that if we can transform these three sectors, we can significantly reduce greenhouse gases emissions. So the transformation in the transportation sector requires replacing gasoline with electricity. For that, we need better electric vehicles, for which we need better energy storage devices, such as batteries and supercapacitors. For electricity grid, our society is already moving toward clean energy sources, such as wind and solar. They are great, they're getting cheaper, but as we know, they are intermittent sources. So if we don't store the energy generated from wind and solar in some sort of energy storage device, we really end up wasting all that energy. So again, we need better energy storage devices. And at the same time, if we can integrate the energy generated from wind and solar with chemical manufacturing via large-scale implementation of electrosynthesis, that can lead to electrification of chemical industries. So the work in our lab is basically focused on developing tools and materials to target these three sectors. And when we say we want to design new materials and optimal materials for any given application, the major challenge is that there is a vast chemical and parameter space that needs to be explored and optimized to find optimal materials. And if we go with the traditional trial and error-based approach of testing each and every material in a lab, it's either going to be impossible to find the best materials or it's going to take us decades. Okay. To overcome this challenge, we adopted the Hollywood approach. And if there are any Iron Man fan here and remember the scene from the movie where Iron Man asked his computer Jarvis to scan the entire periodic table and then find the best element that they needed for their arc reactor. And that's how they discovered a new element. We adopted a similar approach. And not just we, many groups in the materials community actually took advances in theory and computing to accelerate materials design by developing computational infrastructure and databases of computed properties. Some of the very well-known examples are Materials Project, AFlow, Nomad, OQMD, to name a few. However, most of these efforts are focused on using just density functional theory for solid state calculations, okay? Modeling complex liquid solutions and solid liquid interfaces in a high throughput manner is still missing. So the goal of our work is to develop a framework that allow us to predict properties in liquid solutions and solid liquid interfaces over a wide spatial and temporal scale for a vast chemical and parameter space. And for that, we need to combine density functional theory calculations for single molecules and cluster of molecules with molecular dynamic simulations of bulk electrolytes, bulk solutions, and solid liquid interfaces. And then all the computed properties need to be stored in a database so that we can find, we can identify promising materials. So in the infrastructure that we are developing, we have developed actually a lot of easy to use and flexible workflows that allow us to perform these multi-scale simulations in a high throughput manner. So I'll be giving you an example of some of these workflows. So in the MISPR framework, we start with a database of materials, okay? And you can think of it like as thousands of solvents that you want to test maybe in a battery application. We then perform high throughput density functional theory calculations to predict various electronic properties, such as electrostatic potential, electrochemical and chemical stability, etc. We also use these DFT calculations to generate force field parameters, okay, which basically gives us information about different inter and intra-atomic interactions in molecules. And we are developing our own force field databases, which are then used to perform high throughput classical molecular dynamics simulations, okay, both for the bulk solutions as well as for solid liquid interfaces. In this feedback loop, we then extract thousands of clusters from MD simulations, which are then feeded back to DFT calculations for more detailed electronic structure calculations. Okay. Throughout this process, we are basically developing databases of computed properties, which are then used to train machine learning models. Okay. And overall, this infrastructure includes a lot of tedious tasks because we are combining computational chemistry softwares at different length and time scales. So we are using Gaussian for high throughput DFT calculations. We are using Amber for force field development, and we are using LAMMPS for high throughput MD simulations. And each of these software have their own required input parameters, file format, execution command, and the infrastructure MISPR basically automates all these steps and allow user to provide only minimal required input. And this was made possible by building MISPR over existing base libraries in the community. So we are using PyMedGen for molecule representation. we are using a fireworks software for job management, and custodian is an error handler. So let's say if we are running 1,000 calculations and 100 of them, those calculations fail, we don't have to manually go in and fix those 100 failed calculations. Custodian can automatically fix the error and resubmit the job in the workflow so that we can eliminate manual interference as much as possible. And then everything is stored in a MongoDB database for easy retrieval and analysis, and also for the transparency of sharing data. So the centralized infrastructure MISPR is then being used to study properties of liquid solutions, solid-liquid interfaces, as well as solids. And most of our work is focused on energy storage devices such as batteries, supercapacitors, and electrochemical reactors. Okay. This is an overview slide which shows some of the workflows that we have already implemented, and I'll be talking about them. So we have automated workflow to predict the nuclear magnetic resonance chemical shift, workflows for predicting electrochemical and chemical stability, on binding energy between any two species. The workflows for ND simulations allow us to do a lot of structural and dynamical analysis. And finally, we are basically coupling all the data to train machine learning models, mainly to predict properties, which takes a lot of time otherwise with MD simulations or DFT calculations. Okay, so the first example of the DFT-based workflow that I want to talk about is for the prediction of nuclear magnetic resonance chemical shift. If there are any experimentalists here in the audience, you might know that NMR is a very powerful and a very widely used technique to probe structural and dynamical properties for both liquid solutions as well as solids. However, it has its own limitations, and because of low temporal scale and sensitivity, it's often hard to deconvolute this experimental NMR chemical shift and assign them to different structures or stable species which are present in the solution. And this problem becomes even more complex when we are dealing with novel new electrolytes or complex solutions which have a lot of species. Okay, so to overcome this challenge, we developed this framework where we start with just the individual molecule. So all we need to provide is just the atom names and coordinates of a molecule. Okay, and from there we perform DFT calculations, which serves as an input for molecular dynamic simulations. Based on the structural analysis from molecular dynamic simulations, we extract thousands of clusters depending on their chemical environment. For example, if an ion has one solvent or two solvent, or one cation and two anion, etc. From there, we select top clusters, which are then subjected to NMR chemical shift. So here in the NMR chemical shift, workflow, we first perform geometry optimization and frequency calculations. So we relax the structure and we then compute its NMR chemical shift. And then everything is stored in a database so that it can be compared with the experimental NMR spectrum. And to build this workflow, we performed extensive benchmarking of the computational resources that should be used and the parameters that should be used in order to allow to perform these calculations in a high throughput manner. So we use this workflow to study electrolytes that are relevant to battery applications. And I would like to give you an example of this magnesium TFSI salt dissolved in DME solvent. We chose this particular system because it has been studied extensively in the literature to identify its solvation structure, but there are several discrepancies. The previously reported SCXRD data suggest formation of solvent-separated ion pairs, which means magnesium is completely surrounded by solvent molecules. Okay? While the previous computational data suggest formation of contact ion pairs, which means magnesium at least sees one TFSI anion in its solvation shell. Okay, And I want to point out that it's crucial to accurately predict the solvation structure because it controls the properties of liquid, such as its viscosity and density. But this task is not trivial, especially when we are dealing with multivalent electrolyte solutions, such as the ones I'm showing you here. So we use the NMR workflow here to identify most stable speciations which are present in this electrolyte solution. For this purpose, using the NMR workflow, we extracted more than 300,000 clusters. We then categorize them based on their solvation environment and based on their probability of occurrence in the solution. So here the black curve is showing the experimental data, and the bars represents the computationally predicted NMR chemical shift. And this structure 1, which has the probability of occurrence of more than 90% in the solution, matches very well with the center of this experimental NMR curve. And that's the structure where magnesium is surrounded by only the solvent molecule, which was also predicted previously by the SCXRD data. Okay, but the interesting thing about this framework is it not only focuses on this stringal structure that matches with the center of the experimental NMR curve, which has traditionally been the focus of computational NMR studies, but it also allows us to find other stable speciation present in the solution that control the properties of the liquid, but they're hard to identify using experiments alone. So here we identified 5 other stable structures which are likely present in the solution and control the properties of this electrolyte, but we couldn't find them using the experimental NMR spectrum alone. So it's one thing that we were able to predict the NMR chemical shift, but the other most important thing is, can we do it accurately? Because these NMR chemical shifts are very sensitive to a lot of factors, especially in liquid solutions with high degree of freedom. So we identified several different factors which affects the accuracy of NMR chemical shift, such as the parameters that we are using in simulations, the models that we are using, or the conformers, different conformers which are present in the solution. Okay. A key question about MD simulation, or even most of other simulation, is how accurate are our parameters? Okay, so for MD simulations, a key question is about how accurate are the interatomic potential. So we basically compared some of the most commonly used force field parameters in the literature to look at the structural and dynamical properties of this electrolyte. Here we compared 3 different force fields: GAF, OPLS, and OPLS with polarizability. Okay, and we observed completely contradictory results. So for example, if you're using GAF, which is the solid line here, it suggests that we have a very strong cation and solvent interaction, very weak cation and solvent interaction, and a very strong cation and anion interaction. Contrary to that, if we use OPLS force field with polarizability, it suggests very strong cation solvent interaction and almost negligible cation anion interaction. And this can also be seen in the contact ion pair results here. So if you look at the coordination number results for magnesium with solvent versus magnesium with the anion, depending on what force field we are using, we get very contradictory conclusions. If we use GAF, it suggests that we are forming aggregates. If we use OPLS, it suggests that we're using contact ion pairs. If we use OPLS with polarizability, it suggests formation of solvent separated ion pairs. Okay, and that's why sometimes experimentalists don't trust computational people, because depending on what parameters we are choosing, if you're not careful with that, we can get contradictory conclusions, right? So we further extracted all the top 6 configurations from these 3 different force fields. We found that GAF and OPLS shows a very heterogeneous distribution of clusters, where all the magnesium ion have some sort of coordination with the anion, while polarizable OPLS force field shows a very homogeneous distribution of clusters, where cation is mostly surrounded by the solvent molecules. Okay, Based on the comparison with the NMR results that we have and the previously reported SCXRD data, we concluded that it's important to include polarizability when we are dealing with multivalent cations like magnesium, zinc, and calcium, because they have strong electrostatic interactions with the anion, and that can lead to an artifact in the calculations where we are basically over predicting the cation and anion interactions. Okay, another important criteria for accurate prediction of NMR chemical shift is the selection of the level of theory that's being used in density functional theory calculations. So here we performed extensive benchmarking. I'm showing you some of the results for that to identify functionals and basis sets that should be used for these calculations. We use 3 criteria. We select them based on their accuracy, their computational cost, and their tendency to fail. Okay, so we use some of the most commonly used functionals: B3LIP, MO62X, PB1PB, Omega B97X, and 3 Gaussian basis sets: 631 plus G star, 631 plus G star star, and F2TCVP. Now going from left to right, the agreement with the experimental results increases as we increase the basis set. Going from top to bottom, we can see that the choice of level of theory can lead to very contradictory conclusions of the different species that are present in the solution. So based on this and a lot of other benchmarking that we performed, we identified 2 different level of theories, which results in accurate prediction of NMR chemical shift for the type of systems that we are dealing with.
So Nidhi, could you comment on how transferable is this in the end? I mean, you're obviously focusing on a specific chemical shift.
Yes.
But environment,
they're quite transferable. Yes. So these are the high level of theory that we are using, and they of course requires a little more computational cost compared to this lower level of theory like B3LIP 631 plus G star. We used these for other systems like lithium TFSI and also for some of the biomolecules, and they gave good results. So this, I'm sure, so particularly these results I'm showing where we are compared with the magnesium NMR chemical shift. We did similar benchmarking for carbon and proton NMR chemical shift as well. So by combining all 3, we came up with some functionals and basis set that works the best.
And how in terms of your application in mind here, how accurate is accurate enough, or were you actually asking about trends rather than absolute values?
In this particular case, our accuracy was quite impressive because we found a chemical shift difference of like less than 0.5 ppm, which is even acceptable. Even experimental results are not that accurate. So 0.5 and 1 ppm is a really small error that we are talking about. So for these type of calculations, we found pretty good accuracy. I can't say that for every other property that we are predicting.
Good, thank you.
Okay, so yes, and the next step, we also show that how this framework basically reduces the effort of performing and managing hundreds of DFT calculations to a tiny Python small script. And here we computed over 300 carbon and 600 proton NMR chemical shift for hundreds of molecules downloaded from STBS database. We performed complete geometry optimization, frequency calculation using the workflow, and then computed NMR chemical shift using this level of theory. Again, we are trying to use a higher level of theory, even though it cost us a little more. And overall, the infrastructure significantly cut down the time needed to generate the files, submitting the file, and then calculating the errors that we are encountering in these calculations. So on the right, we are looking at the document of NMR document in the database, where we store a lot of information, such as the information about the molecules, its SMILE representation, NMR chemical tensor, and the level of theory we are using, which is extremely important for reproducibility of these type of calculations if other people are trying to reproduce our results. Okay, the second Gaussian-based workflow I want to talk about is for the calculation of binding energy, which is critical for understanding the stability of bond between any two species. So this workflow takes two structures as input. It performs geometry optimization and frequency calculation. And then it basically joins the two optimized structure based on the binding site that's provided by the user. We again perform optimization and frequency calculation, and many of these steps can be skipped. So the workflows are very flexible. And then we finally compute the binding energy, which is stored in its own collection in the database. We recently used this workflow to identify functional groups that should be attached to a solid surface to bind electrolyte species. And I'll talk about these results later in the presentation. Another DFT-based workflow is for the redox potential, which is critical for screening high voltage electrolytes. And there are a lot of possible models and variations exist in the literature for these calculations. For example, we can just calculate HOMO and LUMO energy levels, which are computationally very less expensive, or we can compute the energy level for electron transfer in gas phase or in solution phase, or we can have a complete thermodynamic cycle, which are more accurate but more expensive. Another situation arises when you have a proton donor present in the solution. So if we have, let's say, aqueous electrolytes, in that case, we have to take care of this complete thermochemical cycle, which involves proton-coupled electron transfer process. So the workflow is quite flexible with a tree-like structure, and one can generate as many trees as possible with different combinations. Okay, and basically, depending on what input we are providing for these different theoretical models, we'll save the output results accordingly. So here is an example of a tree where one can perform n electron calculations either in gas phase or solution phase, or using a thermodynamic or thermochemical cycle. And here is an example of a thermochemical cycle for a redox active molecule, and the resulting equilibrium diagram for first and second electron transfer process as a function of pH. So we have been using this workflow to compute redox potential. By now, we have computed thousands of molecules. Here I'm showing results of few hundred molecules, which are relevant to lithium-ion battery application, and include solvents using carbonates, ethers, esters, etc. Again, we have been trying to use the higher level of theory that we have benchmarked to ensure that we have good accuracy in these calculations. Most of the work in the literature has been focused on using HOMO and LUMO energy level, but we found that that leads to over prediction of redox potential. So we used a complete thermodynamic cycle for these calculations. Overall, we dealt with more than 6,000 files using a single script that significantly reduced the time needed to do these calculations. Okay. So are you
sorry to interrupt again, it's just very interesting. So sure. You've got all these molecules, and presumably you've got some combinatorial processes producing them, hypothesizing them for you. And now you have these results. Are you able to sort of look at it and step back as a chemist or material scientist and come up with a sort of like a rational design for improving them?
Yes, yes, I'll come to that. Yes,
okay,
I'll show you an example of that later on. Yes. Okay, so a unique feature of MISPR is that it very seamlessly integrates DFT calculations with classical molecular dynamics simulations. So the workflow for classical MD simulations are built upon DFT calculations. So all the user need to provide is just the structure of a single molecule. We then automatically perform DFT calculations. We use AMBER tools to develop force fields, our own charges basically for force field, and then take bonded and non-bonded parameters from AMBER. But as I mentioned, the force fields are very important for the accuracy of MD simulations. So the workflow is quite flexible. the user can provide their own force field parameters or also take parameters from our in-house database. The next step is where we generate the files, which includes the topology and force field information. And then the user can specify the concentration, ratio of solvents, different mixtures they want to use, temperature, volume, etc. And then we basically generate files for different ensembles with different MD recipes. The default recipe that we are using is first to perform minimization, then NPT calculation, and then NVT calculation. But again, it's very flexible. Everything can be changed depending on the requirement of the user. And then finally, the simulations are submitted. We parse back the output file and the trajectories for statistical analysis. For statistical analysis, we have our own standalone MDProp tool that performs a bunch of different analysis for structural and dynamical properties such as coordination number, diffusion, viscosity, etc. And finally, the MD workflows can be coupled back with DFT. So you can have a hybrid workflow or an independent DFT or MD workflow, depending on the requirement. So here is an example where we used LAMP's workflow to compute structural and dynamical properties for liquid solutions relevant to lithium-ion batteries. And using the workflow, we handle a few hundred of these files. These are on the lower scale compared to DFT to look at the coordination number of different species in the solution as well as their diffusion coefficient. So we are building three main databases. One for the properties computed from DFT, one for force fields, and one for MD simulations. Along with all the properties that we are storing, we are also storing a lot of metadata, which includes the information about the molecule, the software version that we are using, the models and operating conditions, which is very, very important if we want to share these databases with other people and they want to reproduce our results. Okay, so in the next half of this talk, I'll discuss how we are using MISPR and MDProp tool to design optimal electrolytes and interfaces for lithium sulfur batteries. Just to give you some idea, lithium sulfur batteries are considered as one of the most potential candidate to replace the current lithium-ion batteries in future. Because of their ability to provide almost 5 times higher energy density compared to lithium-ion batteries. They can be much lighter, much smaller, and much cheaper compared to lithium-ion batteries. And they're not new. There is more than 4 decades of research going on in this area. And these batteries still suffer from short cycle life. So how many times we can charge and discharge the battery, and poor safety and charging efficiency. So the major problem in these batteries is something called a redox shuttle phenomenon. So when we start using the battery, these lithium ions start migrating from the anode side toward the cathode side. They react with cathode and results in formation of a lot of different polysulfide species like Li2S2, Li2S4, all the way to Li2S8. And that's fine, but then these different species start migrating toward the anode side and result in parasitic reaction at the electrode and in the solution. So that's one of the major challenges in these batteries. The second challenge is where we have to deal with the volume expansion at the cathode. So we adopted a twofold approach to overcome these challenges. We are trying to tune the atomistic interactions in the electrolyte, which is a complex solution, have multiple species in it, to achieve something that will have high safety, low viscosity, and optimal solubility. And at the same time, we are trying to tune the electrode-electrolyte interactions so that somehow we can bind these polysulfide species at the cathode and they don't diffuse toward anode side and result in redox shuttle phenomena. So unlike other battery systems, lithium sulfur battery electrolytes are quite complex. The reason being they have a salt, of course, like lithium TFSI. They also often has an additive, which is typically lithium nitrate. And this is dissolved in a binary or sometimes even ternary solvent mixture. The state-of-the-art system is DOL-DME mixture. And that's the electrolyte solution. But once we put it in a battery, we are forming a bunch of different lithium polysulfide species on which we have no control. So basically, we have multiple species, and it's quite difficult to tune interactions between these multiple species to achieve certain properties. So first of all, we try to understand which of these components affects the solvation structure the most. Is it the anion, the additive, the polysulfides itself, or the solvent? Based on some preliminary work, we found that solvent significantly affects the solvation structure. So we decided to target the solvent and replace this DME solvent with fluorinated solvents. So the fluorinated solvents was recently proposed in the literature as solvents that can suppress the solubility of these polysulfide species, but there is very little understanding of what exactly they are doing in the solution. So we prepared a library of 1,000 fluorinated solvents, out of which only 14 have been tested in the literature so far. The design metric that we are targeting is we want to have a solution with viscosity of less than 2 centipoise, conductivity of greater than 5 millisiemens per centimeter. And this solvent should have high solubility for salt and low solubility for polysulfides, such that we can have high efficiency and cycle life for this battery. Okay. So our approach is to perform a high throughput screening based on several different factors, based on the structural features of the molecules, their thermodynamic and electronic properties, their ensemble properties, and finally a validation from experiments, and also developing machine learning models in the process. But before we start populating our database with the properties of these new fluorinated solvents, it's important to basically assess the quality of the library that we are using, okay? And this is a critical step, especially if you're planning to use these results for any machine learning models, because we don't want our models to be biased toward a specific structure. So for that, we performed path-based fingerprinting to measure the similarity between the new 1,000 solvents that we are proposing and the 14 solvents which exist and which have been tested in the literature, which are here on the y-axis. Okay, so the x-axis shows the similarity measure, where a value of 0 means that two molecules are very different. A value of 1 means that two molecules are very similar. So here we observed a unimodal distribution, which we were looking for, because we don't want our molecules, our new molecules, to be very different, because then we are dealing with a different class of systems. We don't want them to be very similar, because otherwise we won't be able to predict something new. Okay. In the next step, we basically computed different properties, which are categorized into 3 different classes. The derived classes, which basically includes a lot of structural features. Okay, and for each property, we have a measure if we want the property to be at the lower end, intermediate level, or at the higher end. So for example, the properties here in gray, like complexity, van der Waals volume, we want them to be on the lower range, because if the complexity is lower, the molecule will have high synthetic accessibility. On the other hand, properties like proximity between fluorine and oxygen molecule, we want them to be on the intermediate range, because if fluorine and oxygen are too close, it will have high solvating power. If they're very far, they won't be able to dissolve the salt. On the other hand, properties like shape index, we want them to be on the higher range, because shape index indicates a linearity in a molecule. And it's typically known that if you're more the linear molecule, the better are the dynamical properties. So the first class is for the derived properties. Then we have properties which are related to safety criteria computed from Cosmo, like boiling point, flash point, and solubility of the commonly used salt. And then finally, we have the properties computed from DFT calculations, where we are looking at the binding energy with the salt, with the polysulfide, the electrochemical stability, and other electronic property. So this is really the design space we are targeting. We want something that will have high solubility for the salt, LiTFSI, and low solubility for lithium polysulfide. So we want like this optimal balance between them. And this slide basically shows the distribution of properties of all the 1,000 solvents, which are again grouped in derived properties, Cosmo properties, and DFT properties. And we observed a broad range of distribution of these properties, for example, for molecular weight, degree of fluorination, which we're kind of looking for. And we also compared it with the state-of-the-art system, which is DOL and DME, which are these purple cross and red cross here. Overall, we performed more than 18,000 calculations using the MISPR infrastructure. For some properties, we are doing good. For others, we are doing worse. But that's not the end of the story, because we further did more calculations on the screen system. And this approach of carefully computing the properties allowed us to identify some structure property relationships, which helps us in finding the design rules, as Robert was talking about. So, for example, we found that degree of fluorination affects the oxidation potential as well as the binding affinity for the salt. So higher the degree of fluorination result in higher oxidation potential, but in lower binding affinity. So we would want to have an intermediate degree of fluorination to find this optimal balance and compromise between oxidation potential and binding affinity for the salt. We also correlated the binding affinity for the solvent with the polysulfide species and the salt, and they're both with respect to the state-of-the-art system DME, in order to find the design region of space in which the solvent can solubilize the salt, but has lower affinity for these polysulfide species. Okay, so here, the fourth quadrant here, the lower quadrant, is where we can have solvents with lower solubility for polysulfides, but higher solubility for salts. We also developed some machine learning models to predict solubility of LiTFSI salt for new fluorinated solvents, which are not part of the initial library. And we built some convolutional neural network models for that. So this is a parity plot for predicting solubility of LiTFSI for both the training data set as well as the testing data set. And we can see the model is doing decently for the performance metric that we considered, but these are very preliminary results. We can further enhance the performance by increasing the size of the database as well as the library and trying different models. Okay, so based on the derived properties that we have for all the 1,000 molecules, we set some quantitative criteria for ourselves to down select this pool of 1,000 solvents. So starting from 1,000 solvents, we selected solvents only which have salt solubility of more than 1 mole per liter, and let's say electrochemical window of more than 2.7 EVP, and have high boiling point and flash points. So with these different criteria, from 1,000, we down selected to 15 solvents. So here are the 15 solvents, and you would notice that there are actually 18. We included 3 more solvents, which are here in the gray. We included FLS2 and FLS3 because they are commercially easily available. We included FLS4, even though it performs poorly based on our screening criteria. We included it because this is the most used and tested solvent in the literature. And then we performed combinatorial MD simulations for various structural and dynamical properties. And the electrolyte solution that we are using is a good representation of the actual electrolyte in the battery, where we have salt, some additive, we have polysulfide species, we have our benchmark system, which is the current state-of-the-art system with DOL and DME. And we tested it compared it with systems where we are replacing DME with the fluorinated solvents that we are proposing. So here we are looking at the solvation structure. Overall, we found that fluorinated solvents have a weaker interaction with lithium cation, okay? And as the degree of fluorination increases from FLS2 to FLS8, we see weaker interaction between cation and solvent. And this weaker interaction between cation and solvent leads to a stronger interaction between cation and anion. So in fluorinated solvents, we have stronger cation and ion interaction, and this results in formation of some contact ion pairs and aggregates in the solution. So we are compromising on the solubility of the salt. Okay. And we also observe these localized electrolyte where the salt is basically surrounded by non-fluorinated solvents. But we also performed cluster analysis to see what type of clusters and what's the distribution of clusters of lithium polysulfides that we are forming in the solution. So again, the aim was to suppress the solubility of these lithium polysulfide species. And we identified different solvents, which results in large clusters and more distribution of these lithium polysulfide clusters, which indicates that these solvents like FLS2, 3, 4, they are suppressing the solubility of polysulfide, which was something we were aiming for. So along with the structural features, the dynamical properties are crucial for the performance of lithium sulfur batteries. So here we computed the conductivity, viscosity. We also computed other properties, other dynamical properties. One thing and we set ourselves a quantitative metric. We want the conductivity to be higher than 5 millisiemens per centimeter, so this red line, and viscosity to be lower than 2 centipoise. And these criteria are, we set these criteria based on the experimental measurements that has been reported in literature. But what I would like to point out is that those experimental measurements are for the system that do not have lithium polysulfides in them. But an actual electrolyte in a battery contains lithium polysulfide, which increases conductivity, which decreases conductivity and increases viscosity. So the actual numbers that we are looking here are better than the actual performance is better than the numbers we are looking here. But if we still just compare the proposed solvents, we found that most of the solvents that we are proposing have lower viscosity compared to FLS4, which is the most commonly used fluorinated solvent in the literature, and many of these solvents have better conductivity compared to FLS4. So we're definitely able to find solvents which performs better than the ones which are reported in the literature. Based on these results and some other calculations, we down selected 2 solvents, which are experimental collaborators at Purdue and PNNLR testing in an actual battery system. Okay, I would like to also give you a very brief idea of how we are simultaneously trying to tune the electrode-electrolyte interactions to capture these polysulfide species, okay? And one way to do that is by functionalizing the electrode. So we perform some high throughput screening of functional groups that can be attached to graphene and would help us in binding these different lithium polysulfide species. And we tested them for different chain length of lithium polysulfides. And we found some groups like amines, hydroxyl, sulfides, which helps in strongly binding these polysulfide species. So this is a very preliminary work. We are currently working on looking at the solvation structure and dynamical properties of the electrode-electrolyte interface and seeing the comparison of the pristine system with the graphene that's functionalized with different functional groups. So here is an example where we observe that the lower order polysulfide species like Li2S2, the shorter chain, shows some type of layering behavior for functionalized, for graphene functionalized with hydroxyl group compared to these larger chain lengths. And again, this electrolyte consists of different species of the salt, the additive, lithium polysulfide and solvent, but in the picture here, I'm only showing these yellow balls, which are sulfur, just for a clear representation. But again, there's a lot that can be done in this area by changing the density of these functional groups and mixing different functional groups to tune the electrode-electrolyte interactions. So hopefully I was able to give you some idea of the 2 open source code base that our lab developed, MISPR and MDProp tool. We recently made them available on GitHub, so please feel free to check them out if you're interested. We are currently working on their documentation, so if you have any questions, please let us know. And hopefully I was also able to give you some idea how the accuracy of calculations are very important and how we are using these 2 tools to basically developing comprehensive materials databases with properties that we are predicting, and how this also helps in come up with some sort of design rules for electrolyte solutions. So this is, I think, the most important slide. I would like to thank all the members of MolMD group, the funding from LG Energy Solution and Office of Naval Research. I'm very, very thankful to Robert for giving us all the computational resources, because otherwise we won't be able to do any of this. And we also use some of the resources from Exceed. I would also like to thank the experimental collaborators from PNNL, NYU, and Purdue. Most of the work that I presented was performed by the graduate student Rasha Atvi, who's also the main developer of the 2 open source code base that I talked about. With this, I would like to stop, and I would be happy to take any questions.
Nidhi, thank you very much. Let me jump in with another quick question. So you focused primarily on the high throughput aspect of things, which is clearly an absolutely critical and enabling component. But I know you've also looked at some aspects of machine learning. And so and ultimately you're trying to solve this really hard inverse problem, right? You have a forward predictive tool, yes, but you really want to go the other way. So where does AI fit in that?
Yeah. So yes, that's the ultimate goal that we want to do is so right now the main challenge with the things that we are doing is that there is no data. So we wanted to focus on developing generating databases and basically more accurate data that can be used for machine learning models. The machine learning models that we are currently using, I would call it a very naive stage, because we are basically exploring the phase space, okay, and predicting properties, which takes more times with, like, say, MD simulation. So if diffusion coefficient takes us a week to get one data point, with machine learning models, it takes us less than a second. So it's basically a speed enhancement of 10 to the power 5 or 6 times. But the ultimate goal is, once we have these databases, we can basically have some sort of encoder and decoder models, where the decoder can predict the structure based on any given properties. So right now we are in the phase where we have structures and we're predicting properties. Next stage is where we have properties and we want to predict the structure.
Understood. Okay. And so you see, in that sense, initially you'll get an acceleration of the forward prediction, a massive acceleration from the AI, but eventually the AI will give you the inverse.
Yes.
Okay.
Yes.
Okay.
It's a very challenging problem, especially because if we talk about having even 2 species in a solution, because they're changing the properties and predicting not just the structure, but also like the property, the conditions, at what temperature we should operate and what pressure we should operate. That's quite a challenging problem. Yeah.
Let me ask a quick question then. So
Sure.
obviously I'm a developer of electronic structure and other methods, and so these are tools that sit underneath what you're doing, and you're building very significantly beyond that. But what capabilities or refinements to accuracy, whatever, would be useful to you that you don't have right now?
Right. So every time we start with the system, we had to spend a lot of time in benchmarking. And then once we do this benchmarking, then our life becomes easier when we're dealing with more systems. But a lot of time goes in just finding basically the level of theory that can be used in a high throughput manner. So we can't really go for like MP2 calculations, which are very expensive. And we are also not going to develop force field parameters for each and every molecule that's going to work in all temperature range and gives us all properties at different phases. So we have to restrict ourselves to a certain operating limit and do a lot of benchmarking in that region. That takes us a lot of time, but that's the purpose of making this whole thing available to people, so that hopefully they can also contribute and suggest different level of theories that work for a particular class of system. So then other people don't have to spend that time.
And you mentioned that you're open sourcing the software. What about the data?
Yes, we are also open sourcing the
That's
data.
huge. That's unprecedented almost in the community. That's really good.
Yes.
That's good.
So we are in the already made, so for the publications, the NMR work that we did, all that data is open source, and Nature has a really nice tool called Code Ocean. So it's a very nice GUI, which has pretty much everything, all the dummy files. So if one wants to, let's say, reproduce our results, they have to just go and click a button, and in like 2 hours, they will have all the results with all the plots and everything. So
Oh, wow.
yeah, so that's a very nice feature. And for all of the results, we are planning to make the database open source this summer, hopefully.
Okay, very good. Any follow-up questions? Okay, Nidhi, I'm delighted to hear from you again, and it's amazing the progress you're making here. It's I think world leading in what you can do. So thank you very much.
Thank you so much, Rob, and thanks for always suggesting a lot of things. And I know I took a lot of your time.
I learned from you, not the other way around. So thank you. Okay, good. Okay, right. Bye-bye, everyone. Thank you.
Okay, bye, everyone.
Thank you
Thanks,
so
everyone.
much. Take care, guys.